Okay, thank you very much, Barbara. Thank you all the organizers for inviting me here. So in this short half hour, I'm just going to talk about random soliton and soliton gases of KDV. So thank you, Claire, for introducing KDV. I don't need to talk about it. I can skip the first two slides. And this is a collection of some work, and this is the team, the A team that is getting progressively larger as time evolves. So the people that are collaborating on this project. So there is Kanara, there is me, Bob Jenkins, who is in the audience, Ken McLaughlin, Alexander Minakov, and most recently, Guido Mazzucca, who is Ken's postdoc, Joseph Natrodel from Bristol, and Tim Yatselev from Indianapolis. So what I'm going to talk about today is KDV equation that everybody know and love. I just wanted to point out this paper that I recently found that's called The Spirited Horse, the Engineer and the Mathematician. It's basically a recount of what happened when Scott Russell saw this bump into the Union Canal. So it's the whole story. So if you're interested in the history of KDV, this is nice. And of course, the spirited horse is the horse that Maxwell was riding while chasing the bump. The engineer is Scott Russell, and the mathematician are all listed here. There's Airy, Stokes, Boussinesq, Rod Kelvin, all of famous mathematicians of the time. So we know the KDV equation is integrable. It arises as the compatibility condition of the Lax pair, where one operator is a Schrödinger operator, the other operator basically tells us the time evolution of the solution, and then holds the KDV equation. And so from my perspective, I come from the Riemann-Hilbert crowd. So clearly for me, KDV equation is just given as the solution of this Riemann-Hilbert problem. Sorry, yeah. And so this Riemann-Hilbert problem basically consists of some data, which we call the scattering data, that come from the Lax pair equation, from the Lax pair. And it consists of some poles, some values I capital J that are purely imaginary, some constants Cj, which are the norming constants, and then the rho is the reflection coefficient. And so, and you arrange all this scattering data into this boundary value problem that reads like that. So you're looking for a vector solution, vector function, 2, 1, so with 2 entries, that is meromorphic in the complex plane, except on the real line and on these poles. And these points where you have some pole condition, these are the residues that prescribes the behavior of the solution at these poles. And then on the real line, you have a jump discontinuity, and the behavior of the solution on the left side and on the right side, if you take some non-tangential limit, is connected by this jump condition. And you set up some normalization at infinity. So the vector behaves like 1, 1 at infinity plus lower order terms. So in a picture, this is basically the Riemann-Hilbert problem that we want to solve. So we have the poles here on the imaginary axis, on the upper imaginary axis, and then they're kind of like also putting the lower imaginary axis with some symmetry. And then on the real line, we have this jump. So this is my starting point. In the case where we don't have the jump on the real line, so we don't have any reflection coefficient, the solution is very explicit. You just make an ansatz, and this alpha j is a function of x and t, and by looking at how the residues looks like, you can actually find out the solution of this alpha j. And where is the solution of KDV? The solution of KDV is just basically the sum of these alpha j's. Another way to express the solution of KDV from either the Riemann-Hilbert problem is just I give you other 3 ways to write the solution. So you have this very famous K-Moses formula, which is just you put together an n by n matrix. These are the entries of the matrix, and then you calculate a log determinant, second derivative, you get your n soliton solution. Then otherwise, if you don't like linear algebra that much, you solve the Riemann-Hilbert problem. You take the 1 entry, you subtract 1, and then you calculate this limit, x derivative, you get the solution. Or there is yet another way to find the solution of KDV, which was proposed by Gorova, Piotrkowski, and Pesho. If you don't like to take the derivatives, you just multiply the 2 entries of the solution, subtract 1, take the limit, and then you have the n-soliton solution. So there are several ways to find an n-soliton solution of KDV. So the one soliton solution, everybody knows what it looks like. I decided to do with the two soliton just for fun. It's very nasty. But if you plot it, it looks very nice. You see these two bumps and one interacts with the other. Well, it just passes through the other except the phase shift. And of course, from this exact formula, that the K-Moses formula applied for n equal 2, you cannot really tell how the solution look like because it's just a bunch of cosh. What you do is you actually want to do some sort of asymptotics. You want to see how the solution looks like at very negative times, and then you see that you have the sum of two bumps, sum of two single solitons. And when t goes to infinity, you still recover the sum of two single solitons, but there is a shift, which is this logarithmic shift for both of them. And we saw it also in first talk just before, although this is continuous, so it's not discrete. So why do we like solitons so much? Well, because they are localized traveling Willis solutions. They are the eigenvalues of the Schrödinger operator, so they arise also in the long time behavior. And the idea is that you can sort of model initial profiles in experiments as basically a collection of random solitons, right? So that's our motivation. We want to have a lot of solitons and they're random. Okay, so if they're random, if we have a lot of solitons, that's what we usually informally call it as a soliton gas. So I'm gonna just give a brief timeline of what's the concept of a soliton gas from the point of view of just having a lot of solitons that may be or may not be random. So the concept of a soliton gas was introduced in the 70s by Zakharov. He formulated the idea of a dilute soliton gas where you can actually tell all the peaks apart. And he formulated it from the point of view of kinetic theory, where you write down some linear dispersive relations that the gas should obey for the velocity of the gas. A little bit later, Marchenko and some of his students, they started to formulate the soliton gas solution as the limiting solution of the set of multi-soliton potentials. So just from the point of view of like the functional space, you take the set of solutions that are multi-solitons, you close this set. And this is the soliton gas. What you find the limit is the soliton gas. They didn't explore too much this direction. They just started to formulate this, to give this formulation, and they sort of stopped there. In the 80s also, Zeiss and William and separately Boyd, they showed that if you sum an infinite number of such, which is basically the single soliton, this one coincides with this solution coincides with the elliptic solution of KDV. So again, this sort of gives us a motivation that if you sum a lot of solitons together, you manage to recreate several solutions of KDV that were known also independently, like the elliptic solution. It's definitely not the same as a soliton solution. And in 92, I'm also mentioning this paper by Gesesi, Zakharov, and Zhao, where they show that you can have an infinite soliton solution for KDV with provided that you have some conditions on the point spectrum, the poles that are bounded, and the norming constant that is basically L2. So suppose that the kappa J are bounded and then chi squared is in little L1. So this is some of the previous literature, and more recently, of course, there is a lot of interest in soliton gas, and of course, the audience knows about it. And soliton gas has also been observed experimentally. So also from the point of view of physicists, now the soliton gas is getting more and more at the center of research. So let's get back to Riemann Hilbert. So this is where I'm starting from. So we have some poles with some prescribed residues condition. I'm assuming that there is no reflection coefficients. It can be added, but for now we just focus on what happens if we have a lot of solitons that are random. Well, first let's assume what happens if we have a lot of solitons. Period. The randomness will be added later. So this is a case with 4 solitons. So this is an example of a 4-soliton solution. And now let's assume that we are taking a lot of them, and somehow they are all kind of put in between 2 points, ieta 1 and ieta 2. So we're sort of accumulating them in between this interval, and the same also below by symmetry. The only prescription that we have is that the Cj, these norming constants, are accordingly rescaled. So we divide them by n, so they do not explode. And we're assuming that there are the discretization of some sample function R that is sufficiently nice and small. So if you take the limit, eventually you get like an infinite number of solitons. And of course, you can expect that if you fill up this interval in the limit, you recover the full interval. That's exactly what happens. And so you get to a limiting Riemann problem where you don't have residues anymore, you have jumps over these two bands. So this is a paper from 2021 and then 2023. So this is just a recall and a recap of what we've been doing in the past few years. So what do we know about this Riemann problem? Almost everything. So this is a condensate soliton gas, or KDV, using the terminology that Gennady and Alex introduced. What do we know about this? Well, first of all, we have a formula, an exact formula for the solution, so we can write it as a Fresnel determinant, or we can again solve the KDV Riemann-Hilbert problems, take the first entry, subtract one, take the limit, take the derivative. So this formula is still valid, but we also have an exact formula in terms of Fresnel determinant. We also know the long-time behavior of this solution of this condensate gas that looks like this. Is quiescent here, so it's equal to 0. And then you have an elliptic way, an elliptic region on the far left of the real line, and then you have some modulated region in the middle that connects the two behaviors, the elliptic and the quiescent solution. And this is the explicit asymptotic description of all these different regions. This alpha here is the modulated term. We also know that it satisfies a certain Widam equation. We know this was done for KDV, but for KDV can be done as well. We know also what happens if you throw a large soliton inside the gas, exactly like Claire's experiment earlier. And we can calculate all the average velocity and the actual velocity. And we know that the average velocity satisfies the prescribed nonlinear dispersive equations that were already posited by Gennady and Alex. So we know a lot about it. Just in passing, I mentioned that this is a special instance of something that is called primitive potential or Barman potential. It was described by Deschenko, Zakharov, and then Patrick Nabelek also joined the group. And basically, it's this one. This is a numerical experiment that that's exactly this condensate half gas that we analyzed theoretically. And again, I just wanted to mention that I call it half gas here because I have these two bands, but the matrices, the jump matrices are either upper or lower triangular. The full gas is the one that has matrices that are like this. Jump matrices are like full. And this was recently analyzed by me, Bob, and Ken. So if you have more questions, ask Bob or ask me, but ask Bob more. And in that case, we also added a reflection coefficient. So, and also about this full gas, we're starting to know a lot about it. So for example, the long-time behavior. So we could analyze that.
And the functions are one and are two unrelated.
Yeah. In general, it can be any functions.
But before the R was the same R that you were sampling your norming constant set. And in this case?
In this case, they can, so the way we constructed it is we took two different types of solitons, which are actually the same soliton, but one has upper triangular residue, the other one has lower triangular residues, and we sample them in a different way. But ideally, you can sample them with two different, the C and the D. You can sample them in two different ways. So you have two sampling functions, basically. And in the limit, you recover this thing.
So there is no requirement of interlacing of upper lower, or they can.
No. Well, we did it because it was the calculation. We could do the calculations. If you don't interlace, then you can do it. It's just more of a pain. So that's why. But yeah.
So these are one or two, or just smooth function, or they should admit analytic extension a little bit, or no?
Yeah, we would like analytic extension to do some asymptotics.
Okay.
So we assume that they can be extended a little bit outside this band.
It's
So
not necessary. You could do it with C1.
Yeah. So yes, this is again the half gas. So if we get back to the half gas, this one, so we know everything about it in the limit, and but the way we constructed it so far is just by taking like at every step n, you take n soliton and you know exactly where you're putting it. So it's sort of like a limit of a deterministic limit of an n soliton solution. So what happens if, on the other hand, we start with random solitons? So it's the same picture as before with the poles with some residues, but now the way we choose these poles is totally random. So the randomness is injected directly into the spectral problem, into the Riemann-Hilbert problem, not at the initial condition. So it's indirectly to in the initial conditions, but we put the randomness into the selection of the poles. So we assume that they're distributed according to a certain distribution that I'm going to tell you in the next slide. And then we assume that the norming constants, which is the other parameter that appear in the Riemann problem, is again sampled from a function R that we choose, but is sampled according to where it is evaluated. Okay, so the distribution of the norming constants is directly related to the distribution of the poles. It's not independent. So the distribution that we choose for the poles, I'm writing it here, R and T. Oh, sorry, I'm already there.
No, it's fine, Tonio.
It basically comes from random matrix theorem. So we're assuming that the poles are distributed, they have to stay on a line on the positive imaginary axis because the ones that are negative are the position is prescribed. So we're assuming that they're distributing according to the Laguerre-Wishart ensemble. What is that? So take a matrix Y, rectangular, with Gaussian entries, and then IID Gaussian entries, and then calculate this point. So basically, the dagger is the joint. Take the joint types Y, you renormalize so that the matrix, the entries of the matrix do not explode, and then you're calculating the eigenvalues of this matrix. And the distribution of the eigenvalues of this random matrix is given by this distribution. It's very well known. There are lots of results about it, so we know everything about it. That's why we like this distribution. And it's sort of a natural choice simply because for KDV, you cannot have two solitons of the same height and same speed. And this Laguerre-Wishart ensemble sort of mimics the fact that the heights are sort of repelling each other. So these points here, xj, the probability that they're equal is 0. So that's why we decided to choose this specific distribution. And so the question now is what happens when n goes to infinity? So what happens on one hand when the number of solitons goes to infinity, on the other hand when the dimension of this matrix goes to infinity? So what's the distribution of the eigenvalues? We all know what happened. We recover the famous Marchenko-Pastur law that basically, so this is the theorem that says that the linear statistics, that the empirical distribution of the eigenvalues converges to this density function that has a square root at eta 1 and eta 2, which are the two endpoints of the distribution. They're prescribed, they're given by this constant gamma, which is the ratio between the number of columns and the number of rows of the matrix that they're considered. So we know what happens in the limit. So from the point of view of our infinite number of solitons, so all the solitons eventually they accumulate into this interval between eta 1 and eta 2. So they don't get too close to 0, they don't run away to infinity. So already from here, we can already expect that if you have a random soliton and soliton solution with the poles distributed like that, eventually take a lot of them and they concentrate into a band and you recover the gas condensate. So this is what we did. So basically, how do we prove that you have in soliton you can converge to the condensate? Well, you encompass all these solitons, all these poles into two big loops. The only technicality here is that you need to make sure the poles are still inside the loop. The poles are random, and at finite time they can technically escape, be very big, or be very close to 0. So we need to evaluate what's the probability that the largest pole and the smallest pole are still within the loops that we're choosing. And this can be done using some orthogonal polynomial strategy, and it turns out that these probabilities are exponentially small. So we can do that. We can collect all the poles and put them into a loop. So we transform a residue conditions into jump conditions, and then we take the limit. And the jump conditions, the matrix in the jump, the entries in the jump have this particular expression, which looks a lot like a local statistic, like a linear statistics of some distribution. And when we take the limit, we know that this converges to the Marchenko-Pastur law. So now the last problem is that, okay, now we know that the Riemann-Hilbert problem at finite time converges to the Riemann-Hilbert problem with infinite solitons. Now now we want to compare the potentials. So we need to do a small norm analysis. So we take the finite time solution of the Riemann-Hilbert problem, we take the infinite solution of the gas Riemann-Hilbert problem, and then we combine them this way, and we want to calculate the remainder problem. So here notice that I need a matrix Riemann problem if I want to do that. I want to take the inverse of something, I cannot take the inverse of a vector. So again, another technical step is how do you go from a vector to a matrix Riemann problem? Well, we need to generate a second solution of KDV and stack the two rows together, we get a matrix. But eventually this matrix will have a singularity at zero, at z equals 0. So we will have, but the remainder turns out to be regular. So all the asymptotic analysis pushes through. So that's nice. And the idea is that Qn minus Q infinity, so the difference between the potential is basically given by the one entry, the first entry of this remainder problem. So all the information are encoded into this object. So for those of you who don't know Riemann-Hilbert problem,
So
how do you do?
Qn is random and Q infinity is deterministic.
Deterministic,
Okay.
yeah. So what we have to analyze is this random Riemann-Hilbert problem. And in the asymptotic limit as n goes to infinity. So when you want to do asymptotic, the two tools that you have is small norm theorem. So assuming that you have a Riemann-Hilbert problem where the jumps are asymptotically small, the solution is asymptotically close to the identity with these small terms that they can be explicitly written. And then if you're not in a small norm theorem, then you have to do some Dispersive method to get back into the small norm theorem. In our setup, we don't need Dispersive because we're already in a small norm theorem, but the small norm terms are random. So we need to estimate when do they happen to be small and when do they not happen to be small in probability. So this is our setup. We're in a small norm theorem, we're in a small norm setting in certain conditions, and we need to estimate that the probability that the random terms are not small is small. It turns out that it is exponentially small. So with high probability, you are always in a small norm theory. So therefore, this E1 is actually what gives you the comparison between the finite and random potential and the infinite potential that is deterministic. And everything depends by how fast this linear statistics converges to the Marchenko-Pastur distribution. So these are the results. So you have to work a lot on the probability side, not so much on the Riemann-Hilbert side. So we managed to prove that the finite time potential converges in probability to the infinite condensate gas. We managed to prove that it converges also in mean, and the variance goes to 0. So it basically tells us that you have a random n soliton solution. This converges to a deterministic solution. You have no variance. Everything is frozen. Ingredients of the proof. Maybe I'm going to skip it for the interest of time, but the idea is that, yeah, you work a lot with probability estimates. And the last thing to ask is, what about local fluctuation? So these previous two results are basically some sort of law of large numbers sort of result. So now the next question is, what happens if you look at the local fluctuations around your limit? And you're sort of expecting a sort of central limit theorem, so you're expecting to find Gaussian fluctuations, and that's indeed what happens. Why? Because if you look at the linear statistics for the Laguerre-Wishart ensemble, you have a central limit theorem. So you know that you take the linear statistics, you subtract the average, you get some normal random variable with 0 mean and some prescribed variance. So we translate this result into our Riemann-Hilbert setting, and we translate it back into our potential setting in what we actually want to analyze, and this is what we get. So I didn't write the formula, but indeed, if you take the n soliton solution, you subtract the infinity, the gas solution, you multiply by n, this converges to a Gaussian random variable with the 0 mean, and then the variance depends on the position. And this is just a simulation. So this is the last result that I wanted to show you. And let me just wrap up. So what do we have so far? So I showed you several pieces of the puzzle. So we're starting to understand more and more what is going on with these condensate gases for KDV. So this is a new class of solution for KDV. It's a condensate gas, it's deterministic. We know what happens in the large time regime. So we know how the solution looks asymptotically for this condensate gas, and we know that it's a universal limit of a large class of random n soliton potential. So here I showed you that the poles are sampled according to Laguerre-Wishart distribution, but it can be sampled according to other distributions. For example, uniform in a band, the band and without. And similar results are also obtained for NLS, for focusing NLS. This is, for those who were here 2 weeks ago, this is what Tamara showed. The only difference with FNLS is that in our case, we could assume that the distribution of the poles at the finite end, they could be on the whole real line, because we know that eventually they concentrate very fast into the band. For FNLS, we tried with Ginebra, which are potentially distributed on the whole upper plane, but in that case, the concentration is much slower, so that didn't work. So we had to sort of introduce cutoffs. And also the difference is that for FNLS, you have much more freedom over where the poles distribute and they concentrate. So you might not get a condensate after all. But for KDV is more, the geometry is more restricted. So you always get a condensate in here. These are a lot of more problems to work on. So the story is not over for sure. So we can add more randomness in the coefficients, for example, that right now are so deterministic based on the poles. We can study more this generalized gas because so far we only know the asymptotic behavior, the long time behavior. We don't know, for example, what happens if you have a big soliton that goes through it. We can try to construct new gases. And then this is, I'm just flashing you with this picture that is very much work in progress, but is one of the latest studies that we've done, again, with Bob, Tamara, Ken, Guido, and Maxime, where we're studying NLS, and we have a soliton train. You can think of a dilute soliton, and we let them all smash at some point, and there is a big spike. And we see some universality profile that appears there. And I stop here. Thank you very much. Sorry for that.
What are the parameters in the probability distribution?
Basically is the gamma. It's just so here we're taking beta equal 2, just complex Wishart, and so basically the n times n. M over n is the gamma that in the end it gives me the endpoints. So that's the only parameter that we have here.
So okay. 2 questions. So is there a physical reason why you've chosen this particular distribution of spectra? I mean, some heuristics, even just heuristics, or is just it's the simplest?
No. So the original idea was that we know that poles cannot, you cannot have 2 solitons with the same height, so they're kind of repulsive. So we wanted some distribution that is on the whole positive axis, and it is repulsive. And so that's the first thing that came to mind.
But if I understand that the technical results does not specifically require that is Marchenko-Pastur, it's just that there is a limiting distribution.
Yeah.
Right? It could be another matrix model with
yeah, it could be another matrix model that that has a limiting distribution, is compactly supported. That's fine.
Do you expect the result?
We expect the result to still goes through. So this is the only part where here we heavily use the fact that the Laguerre-Wishart is determinantal twin process. So these are gap probabilities.
But I think this is true also if there are several gaps outside of the bulk, which I think it's still true.
Yeah. What I'm saying is that I want a distribution that has a determinantal structure. Then we can easily estimate these gap probabilities. If it's not determinantal, there is a little bit more tricky.
And in this example, the Riemann-Hilbert problem, the associated Riemann-Hilbert problem still has the upper-lower triangularity with the same function R. There's only one
there's
function
only
R
one
here,
function.
but
Yeah, this is the
in
half
principle, you could do the same thing for the.
That's on our to-do list. Yeah, so this is only the half gap, so only one triangularity.
So you mentioned the distribution of the eigenvalue, the poles, and the distribution of knowing constants kind of rigidly connected.
Yeah.
And this is condition for the construction to go through.
Yeah.
So
But-
I could guess if you kind of disconnect them, somehow you get truly, you can get truly random gases.
Yeah, you get even more randomness. Yeah, so.
And
Yeah,
this is kind of
if you're
probably
assuming
the
the
core
CJ,
that you're getting at the end, you're getting still deterministic regular gas.
Yeah.
This is kind of rigid.
Yeah. So I agree that if we manage to introduce randomness in the CJ, then we will have to Well, it's you will have to consider like the joint distribution and the
And
marginal
not
formula.
condensate,
It may not be condensate, yeah.
for sure.
Well, then the condensate also arises because you're dividing by n. So, definitely, if you're assuming the CJ are completely disconnected from the poles and do not scale like n, yeah, then there is a zoo over there. I
Yeah,
have
that's-
no idea what you get, yeah.
Okay. Thank you,
Thank you.
Manuela.